Good morning, friends. Today we will have another tutorial session. The first question is, determine the Laplace inverse of factorial n divided by s into s plus 1 into s plus 2 up to s plus n. Okay. So, easiest method is to find out the partial fractions. I will write a0, a1, a2 by s plus 2 and so on, ak by s plus k general term. Okay. So, how much will be a0? A0 multiplied by s, this fs, make s tending to 0. So, that gives me factorial n divided by 1, 2, 3, 4 up to n, that is equal to 1. A1 multiplied by s plus 1, make s plus 1 equal to 0. So, what do I get? A1 as 1 into 1, 2, 3, 4 up to n minus 1. So, that gives me n with a negative sign, because the first one will be minus 1. A2 will be factorial n divided by multiply by s plus 2, then make s plus 2 equal to 0. So, it will be minus 2 minus 1, minus 2 minus 1, then 1, 2, 3 up to n minus 2, and that will give me plus n into, see, I get minus 1 minus 2 n minus 2. So, factorial n divided by factorial n minus 2 into factorial 2. A3, and what is this? You can identify this as NC2. A3 similarly will be factorial n divided by minus 3 minus 2 minus 1, then 1, 2, 3 up to n minus 3. So, I get minus 1 into factorial n by n minus 3 factorial into factorial 3, that is NC3 with a minus 1. So, alternately the signs are coming plus 1 and minus 1, and these are combination terms. So, this can be written as, therefore, Laplace inverse of factorial n by s into s plus 1 etc. up to s plus n as factorial n. So, I can straight away write NCR minus 1 to the power r e to the power minus rt, because it is a0 into ut, a1 into the power minus t, a2 into the power minus 2t and so on. So, it will be e to the minus rt, r varying from 0 to n. So, this is nothing but 1 minus e to the power minus t to the power n. Okay. So, this is the response. There is a function given fs equal to 10 by s squared minus 10 by s into e to the power minus s minus 10 by s squared into e to the power minus s whole thing 1 plus e to the power minus s. What will be f t like? Whenever you come across terms like this, it signifies basically a periodic function. Okay. So, let us first of all consider only this bracketed quantity. Let f1s be this bracketed quantity and let f1t be the corresponding Laplace inverse. So, what is the function 10 by s square giving me? f1t will consist of the inverse of this, this and this. What is 10 by s squared? It is a ramp function, okay, of slope 10. I will write slope in terms of this, minus 10 by s. So, 10 by s minus 10 by s. So, this is e to the power minus s. So, at 1 second we apply a step of 10 volts, negative step, and then minus 10 by s squared e to the power minus s. So, again at 1 second we apply a slope of minus 10. What is the summation of these three? Summation of these three will be giving me net value f1t. These are all in the t axis, and these are the three components of f1t whose Laplace transform is this. So, f1t will be this one till it gets interrupted by the second part, which is a negative step, and again a negative ramp. A negative ramp will try to counter the increase. So, it would have, if I take this plus this, it would have been a function like this, but then there is a negative step of the same magnitude. See, after 1 second this goes up to 10 volts, this goes up to a magnitude of 10. So, then it would have remained constant if I apply just a negative ramp of slope 10, but then there is a negative step also of minus 10. So, it will be coming down to 0, and this will be the net value of f1t. Okay. This is f1t, this thick line. Now, let us see what is f1s finally giving me. If we want to compute fs, this f1s, in what way it is being repeated? 1 by 1 plus e to the power minus s comes out of a series e to the power minus s plus e to the power minus 2s plus minus e to the power minus 3s and so on. If you have alternately changing signs, then only you get, that is a common ratio of minus e to the power minus s. If this is the common ratio, then the geometric series will give me a series like this. That gives me f1s minus f1s into e to the power minus s plus f1s into e to the power minus 2s and so on. Alternately, f1s is shift with a shift of 1 second, 2 seconds and so on. Alternately plus and minus will give me fs. That means, correspondingly f1t, if I take alternately plus and minus, that will give me ft. So, ft will be this f1t, then after 1 second it is negative, then positive, then negative and so on. This will be the nature of ft. Okay. Next, there is a question there is a Bode plot where at 20 there is a break, this is omega 2, this is omega 1, this is 6 dB and this is 30 dB. This is 20 dB per decade and this is minus 20 dB per decade. Calculate omega 1, omega 2 and the function Gs So, what will be the Bode plot like? Gs, what will be the form? Some constant times at omega equal to 20 it is going up. So, it will be 1 plus s by 20, okay. This is omega in radians per second, 20 radians per second. So, 1 plus s by 20 will be this. Then at omega equal to omega 1 there is a fall of 20 dB becomes minus 20 dB. So, there is a fall of 40 dB. So, 1 by s plus omega 1 whole square. The whole square term will give you a slope of 40 dB per decade. Is that all right? And then at omega 2 again that is restored. So, 1 plus s by omega 2, this will be the 1 plus s by omega 2 will be the other factor which will finally make it horizontal. Now, what is omega 1 and omega 2? 20 dB per decade is the slope. So, 20 dB per decade can be written as 6 dB per octave. That is, it is getting doubled every 6 dB. So, 30 dB means 5 into such 6 dBs are there. Okay. So, this can be written as 30 dB is 6 into 5. So, there are 5 octaves from 20 which will take me to omega 1. So, omega 1 will be 20 into 2 to the power 5. Is that all right? So, 20, one octave will make it 40, next octave is 80, next octave is 160 and so on. So, it will be 640. Again, how much is this fall? 30 and 36, 30 plus 6, 36. Okay. So, this is an approximation because 6 dB per octave is also an approximation of 20 dB per decade. Omega 2 should be 36 means 2 to the power 6 into omega 1. From omega 1 there should be 6 such octaves. So, that means 2 to the power 6 into omega 1 and 2 to the power 5 into omega 1, that is 20. So, 2 to the power 11 into 20. So, whatever be that value, this will be the approximately 40960 radians per second. Okay. If one goes by the actual value, then it is 30 dB is 20 plus 10 dB. So, 20 dB means 1 decade. So, that gives me in terms of frequency omega 1 is 20 into 10 and 10 dB will correspond to root 10. Okay. So, this is approximately 628 radians per second. Instead of 640, you should get 628, and 2 to the power, instead of 2 to the power 11, if you take this is 30 and 30, 60 dB up to this and then 6 dB. So, if you take 66 dB that way, it will come to about 40 K. About 40 K. Next, we have another question. The Bode plot of a network function Ys is shown like this. For Ys, some Ys, this is minus 30 dB, these are all 20 dB per decade slopes. This is 5, 10, 20, 40. This is 0.2. These are not to the scale exactly. This is 0.2 minus 30. What will be the value of Ys? And the next question is it defining a driving point impedance or admittance function? Is it a driving point admittance function? If not, justify. If yes, state the reasons and then realize one in Foster 2 form. So, if yes, then realize in Foster 2 form, and if not, justify why it is not a driving point admittance function. Let us write Ys, the nature of Ys. It will be k times, there is a function that is going up. So, the factor corresponding to that is S. Then the 20 dB per decade slope is made horizontal, that means there is an addition of a term 1 plus S by 5. Okay. This is in radians per second. Then 1 plus S by 5. Numerator again it will be 1 by S plus 10, 1 plus S by 20, 1 plus S by 40. Okay. Before we go into the evaluation of k, let us see k is just a scaling factor. Is this an admittance function, driving point admittance function? Yes, because zeros and poles are coming alternately. If I simplify this, it will be S plus 10, S plus 40, S plus 20, S plus 5. So, if poles and zeros are coming alternately and if the difference in degree is restricted to 1, then it will be possible to realize this as RC or RL. Okay. All the roots are in the negative on the negative real axis. Is it an RC or RL? It is an Ys function and S is coming in the numerator. So, this is an RC, that is root closest to the origin is 0. If it is 0 for an admittance function, it is an RC network. Now, you can evaluate K very easily at 0.2, at s equal to 0.2. When we are making a Bode asymptotic plots and making calculations on that basis, we neglect the effects of higher frequencies at such low frequency. So, at 0.2 basically these are all negligible terms. So, these will all reduce to 1. So, K into s equal to j 0.2, K into j 0.2, 20 log of this magnitude is equal to minus 30. So, that gives me 20 into log of k plus 20 log of 0.2, 20 log of 0.2 is equal to minus 30. So, you can calculate k from here. All right. So, k turns out to be 0.158 approximately. So, ys is 0.158 into s into 1 plus s by 10 into 1 plus s by 40 divided by 1 plus s by 5 into 1 plus s by 20. So, that gives me, if I multiply by this 10 and 40, 400, 20 and 500. So, 4 times this, 4 will come in the denominator. So, 0.039 s, okay, into s plus 10 into s plus 40 divided by s plus 5 into s plus 20. If I Foster 2 means you break up ys. So, it is k1 into s plus k2 into s by s plus 5 plus k3 into s. Should it be s? Okay, k3 into s by s plus 20 is an admittance function. So, that turns out to be 0.039 s by the usual method of partial fractions, 11.66 s by s plus 5 plus 13.33 into s by s plus 20. Correct me if I am wrong. So, that gives me a capacitor of value 0.039. If you permit me, I can write this as 0.04, an approximation, plus 1. So, 0.04 s, and then this is an RC, this is also an RC of corresponding values. If you take s to be, you just invert it and then put the values. This comes out to be 0.43, that is 5 by 11.66 and 1 by 11.66. So, that gives me 2.32 farads. Okay. And then this one comes out to be 0.075 ohms, and this one is 0.67 approximately farads. So, this is the realization. Next example that we shall take is on a filter. Determine the values of L and C for a low pass filter. Low pass filter, RK is equal to 500 ohms and cutoff frequency 60,000 radians per second. Okay. You have to calculate also alpha at 15 kilohertz, beta at 5 kilohertz, and thirdly, if I have an M derived filter, the value of M for getting f infinity at 12 kilohertz, that is attenuation should go to infinity at this frequency. What should be the value of M? What should be the value of M? So, the relationship is well known for a low pass filter. You know Z1, Z2, you take the products, so FC is given as 60,000 divided by 2 pi. Okay. L, how much is L? RK by pi FC. Okay. RK is 500. RK is 500 and pi into FC, 2 pi FC is 60,000, so 30,000. Correct me if I am wrong. All right. So, that gives me 0.0167 Henry. What about C? Similarly, C also you know the relationship for FC, L and C. C comes out to be 6.68 into 6.66 or 67 rather, 10 to the power minus 8 farad. M in the usual way 1 minus, how do you calculate M? What do you put for M? 1 minus F by F infinity squared, okay, 1 minus, how much is F, or how much is F? Sorry, this is FC, FC by F infinity. FC is 60,000 divided by 2 pi and F infinity is 12 squared. So, that turns out to be 0.6 approximately. All right. Alpha and beta. Alpha is 2 cos inverse. You have to calculate alpha for 15 kilohertz. 15 kilohertz. All right. Mind you, this is given in kilohertz and this is given in radians per second. So, divided by omega by omega c. Okay. So, either you multiply this by 2 pi and 60,000 2 cos inverse omega by omega c. So, that gives me 2 cos inverse 30 by 60. So, pi by 2. Mind you, this is 15 kilohertz. So, into 10 to the power 3. So, 10 to the power 3 will get cancelled. So, pi by 2. So, that gives me a value. If I multiply by 8.68, this is in NEPA, 8.686 into this quantity, that will be giving you the value in dB, that is 17.76 dB. This is approximately 2 point something, 2.1 or so. So, approximately 17.76 dB. Beta 2 sin inverse omega by omega c to sin inverse beta you have to calculate at 5 kilohertz. So, 2 pi into 5 into 10 to the power 3 divided by 60,000. So, that gives me in radian 1.1 radian. This comes out to be 1.1 radian. All right. So, these are the values of alpha and beta. Next, we have a question on a network graph. You are given a network. This is example. You are given a network like this. This is node number 0, 1, 2, 3. This is carrying a current I1, I2, I3, I4, I5 and I6. Sorry. You are asked to calculate, first of all, draw an oriented graph, and considering 0 as the reference node, determine matrix A. Okay. Considering 0 as the reference node, determine A. So, let us complete these parts first. So, I will draw the network graph like this. Basically, it represents it is not in the same plane, not coplanar. 0, 1, 2, 3, and elements are numbered as the current element, that is, this is as 1, this is as 2, and the direction is also the direction of the current, we choose 3, 4, this is easy to comprehend, 5. So, this is the network graph. Then, by choosing 0 as the reference, you can very easily write matrix A as elements are 1, 2, 3, 4, 5, 6. and the nodes are 1, 2, 3, 0th node is absent. So, the bus will have the matrix A will have element 1 coming out from 0 entering at 1. So, this will be minus 1 0 0. Element 2 is from 1 to 2. So, plus 1 and minus 1, plus 1 minus 1 0. Okay. Then element number 3 is 2 to 3. So, 0 1 minus 1, at 2 it is plus 1, at 3 minus 1. Element 4 3 to 0. So, 0 0 1, at the 0th node it is minus 1. So, the 0th node is not present. Then element number 5 is 1 to 3. So, 1 0 minus 1. Element number 6 is 2 to 0. So, 0 1 0. Okay. And then the next question is, for this network graph, determine the total number of trees. Total number of trees is equal to determinant of A transpose. If A transpose, determinant of that is equal to the total number of trees, what will be the total number of trees for this particular example? So, it will be A transpose is minus 1 1 0 0 1 0, 0 minus 1 1 0 0 1, 0 0 minus 1 1 minus 1 0, minus 1 0 0 1 minus 1 0 0 1 minus 1 0 0 1 1 0 minus 1, then 0 1 0. So, that gives me minus 1 into minus 1, 1 into 1 and 1 into 1, 3, then minus 1 into 0, 1 into minus 1 and then 1 into 0. So, minus 1. Similarly, this into this gives me 0 0 0 0 1 and minus 1, okay, and minus 1. This will also be 3. We can see this will be always a symmetric matrix. So, once you have got these values, you can fill up this. Similarly, if this is known, then this will be known. And I have just computed just now, seen there are only 3 elements, 3 non-zero elements. When they are multiplied by the corresponding elements here, they will be getting plus 1 plus 1 plus 1. So, you have to count, actually you have to count how many non-zero elements are there. So, so many plus 1s will be in the diagonal elements. So, that gives me 3 into 9 minus 1. So, 3 into 8, then minus 1 into minus 1 into minus 1 plus 1 into this. So, that comes to 24 minus 4, so 16. That's 4. So, total number of determinant this, sorry, this into this is this matrix, determinant of that is 16. So, the total number of trees will be 16. Okay. Next, calculate QF, fundamental cut set matrix, converting A to a unity matrix. All right. Part of A by unitary transforms. So, you have got A as minus 1 1 0 0 1 0 0 minus 1 1 0 0 1 and then 0 0 minus 1 1 minus 1 0. So, very simple transformation. I want q, I want 1 here. So, if I add this with this with this, that means row 1 plus row 2 plus row 3, I will call it sum A 1, row 1 plus row 2 plus row 3, okay, replacing row 1, and then negate the sign. So, I get minus 1 0 0, and if I change the sign it becomes 0 1 0 0, all right. This is the tree element, and then here it is 1, so that becomes minus 1, this becomes 0, this becomes 1, so minus 1. Then this and this, if I add, this becomes 0, this becomes minus 1, and if I again change the sign, so 1 0, then this becomes minus 1, then this and this becomes plus 1, this becomes minus 1, and then this one I just change the sign, I get 0 0 1, then minus 1 1 0, okay. And if I find, I get a unity matrix here, this itself is QF. So, the transformation is very simple. So, I have got from A directly QF by a simple manipulation. One may question whether this is representing a tree, this part of A is representing a tree. Yes, that has to be verified because the diagram is very simple. So, you take, these are the nodes 1 2 3 1 2 3, okay, from A matrix. If you take 1 2 3 elements 1 2 3, that forms a tree. Actually there are 16 possible trees. You take any three combination which will not make a loop, that will be a tree, because there are only 4 nodes, so 3 elements will require 4 nodes. So, you make any combination of 3 elements, you will find this is an interesting figure. Any combination of 3 elements without forming a loop, without forming a triangle, that will be a tree, and there are 16 such possibilities. Could you draw the trees, all those possible trees? Let us see for this example what are the possible trees. We can have 1 2 3, this is 1 2 3, I will not number them. Then its counterpart is 1 3 4 is another tree. Then 4 2 1, 2 3 4. So, if one may write 1 2 3 1 4 3 1 2 4 2 3 4, okay. Then 1 5 3 1 6 3, okay, 1 5 3 163, then 264, then 254. And so on. You can make a few more. Could you suggest? 135, 136 and so on. And I leave it as an exercise. All of you can try all other possible trees. Okay. See the other possibilities, 1 or 2. Could someone suggest? Yes, this one, next, this one, next, this one, okay, this one, then is there any other possibility? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 4 more are there, 4 more possibilities are there. If I take this one and this one, then I can have only this one. I cannot fit in the other one, that will make it the triangle. All right. If I take 1, 2, there seems to be 12 only. What are the other possibilities? One, 2 and 3. 1, 2 and 3. 1, 2 and 3. 1, 2 and 4. So, these are the 16 trees. Okay. You cannot have anything more than this, just 15 trees, 16 trees, right. It is better if you keep on drawing for any graph the possible number of trees and verify the relationship. If the number is too big, of course, it is very difficult, but you have to imagine what are the different ways you can form a tree by connecting different nodes without forming a loop. Mind you, there are chances of making errors here. There is no node here, all right. It is, the lines are one over the other, they are not connected here. Next time we shall be taking up a 2-port synthesis. That is, if you are given a network function in terms of say V2 by V1, V2 by V1 will be a transfer impedance or transfer function. It may be V2 by V1 or V2 by I1 or I1 by V2, I1 by I2 and so on. That means, you may be given the specifications either in terms of Z12, Y12, Y22 and so on, and Z11. So, specifications can be given in terms of Z11, Z12 or Y12, Y22 or V2 by V1 and so on. You have to determine a possible network. So far we have studied the driving point synthesis. Now, we shall be going for 2-port synthesis with transfer impedances. Okay. Some of the basic conditions for these impedance and admittance functions, that is the transfer impedances and transfer admittances, are very interesting. And so, for transfer function also, we will find the numerator and the denominator polynomials ns by ds. They need not have all the properties that were listed in the driving point synthesis, that is, the difference in degree can be more than 1, difference in degree can be more than 1, can be, may or may not be, but ds must be a Hurwitz polynomial, roots must be always in the left half plane. So, ds must be Hurwitz. There can be multiple roots, multiple zeros on ns, there can be all possible combinations. So, we shall study in details what are the conditions to be satisfied for two port synthesis, what are the conditions for y11, y12 or z11, z12, this pair of admittance or impedance functions. Thank you very much. Good morning friends. Today we will be discussing about two port network synthesis. You know, in case of a two port, you have various specifications. You may have for a two port network y11, y12, y22, these are the parameters, or maybe a, b, c, d, or z parameters and so on. These are the three commonly used sets. Sometimes you may be given only a gain function g12, which you know is given by this, or minus y12 by y22. So, if this voltage by this voltage, this is the gain function, only the gain function is given, then you are asked to realize a network to give that particular gain function, all right. So, the specifications can be many types, unlike a one port network where you are given either Zs or Ys. Ys is just inverse of Zs. So, you have one specification. Here the specifications can be in terms of say y11 and y12, or y22 and y12, any two can be given, or maybe just the gain function, all right. So, how to realize a network to meet these specifications. So, before we go into that, we will just see the network functions, how they are related to these two port parameters, network elements. Let us take a T network, okay, or a pi network. From a T you can always find a pi. This is star to delta or delta to star conversion, all right. Normally, if you are given the specifications in terms of Z parameters, you go for an equivalent T, this is easier. Similarly, for Y parameters we go for pi network. Suppose this is given as Ya, Yb and Yc. What do you mean by zeros of transmission? Transmission zeros means what? I give a signal, at the other end nothing is received, is it not? Now, in how many ways that can be ensured? I give a signal, you take a water pipeline, all right. In what are the different possible ways the say delivery of water at the other end can be disrupted?
So, there is a big leak in the pipe.
Very good, there is a leakage. So, water is grounded, basically the pipe is grounded, the entire pressure is grounded. Is there any other way of blocking? So, if you have some blockade in the series path or a short circuit in the shunt path, then you have a zeros of transmission. That means, how do you create a zero of transmission? By short circuiting. At some frequency, suppose at some frequency I find a squared plus 9 in the numerator, that means at s equal to j3 this a square plus 9 will be vanishing, that is a 0 at that particular frequency. So, at that frequency I want there should be no transmission of signal, and I want short circuit at that particular frequency.
So that it will
No, a short circuit means what? It should be a series resonance. If I have a series resonance at s equal to j3 and that element is put in shunt, okay. So, you are having an element like this, there are many such elements. In the ladder I create this element is say an LC combination. Thank you very much. That is why this scaling was very, very important. So, in any case you can weaken this to shift it to either 1 or 2. Okay. Thank you. So, in that case what will be this one? Z11 double dashed at J2 should be equal to 0. This is a 0 which gives me, yes.
we won't weaken the pole at 4, we will weaken the pole at 0. So not K2 dash S by square plus 16. And when we K2 dash S.
Sorry, we are weakening the pole at the origin.
Yes, sir.
And
when we weaken it, the pole at 0 at 3 will tend to 0 at 2.
Yeah.
So we should write the impedance function.
That is what I am putting J2.
Z11 at J2. Z11 dash at J2.
I am going to write that. That is what I am going to do. This will be Z11.
Z11 double dash is by weakening the pole at 4. Yes.
Okay, let us write it here. Okay, we will continue with this in the next class. The time is over. We will continue with this in the next class. Thank you. This is only for